So I had a couple questions I actually got asked this morning, so I'm going to answer those first. First is considering the 4n+2 rule. So both of these are organic 2 questions. The first one considers the 4n+2 rule and how do we actually count the number of electrons that are in there. So let's say we have two molecules like this. So we have cyclopentyl, diene, CP, and then we have the cation version of it. Now, to figure out aromaticity, you're going to see this with the discussion board. The best thing to do is actually go through and make sure that you meet the first 2 requirements, because the 4n+2 actually requires real work on your part. So in order for something to be aromatic, it has to meet 3 conditions. First, it has to be cyclic. 2, it has to be conjugated. And 3, it has to meet the 4n+2 rule. So this conjugation here, how we verify whether molecules is conjugated, this is going to play a role in how we do the 4n+2 accounting. So this is a conjugated system because we have pi bonds that are conjugated, they're connected, but in place of a pi bond here, we're going to use this carbon here. This is going to be a vacant p orbital holding the carbocation. And the same thing is going to be true for this molecule as well. We've got the conjugated alkenes, and then we've got a cation or a lone pair or something that we can use a vacant p orbital for. So if I had an oxygen in this case, I can put an oxygen there and use one of the lone pairs. This is going to show up in the accounting. So now what I have to do to figure out the number of electrons is the first thing I'm going to do is take the number of pi bonds, multiply by 2. So each pi bond here contains 2 electrons, and since they're part of this aromatic system, they're going to add towards their electron count. Now, if I have a lone pair, so let's say I have tetrahydrofuran. I have my conjugated alkenes, and then I'm going to use, for each atom containing a lone pair, I can only use one set of lone pairs. So I can't use both the lone pairs and oxygen, but if I want oxygen to be part of the conjugated system, I do have to use one of those lone pairs. So it's 2 times the number of pi bonds plus 2 times the number of lone pairs, or the number of lone, or just the number of lone pair electrons, plus 2 times the number of anions I'm using. So if I'm using an anion to kind of bridge these alkenes, I'm going to count that towards it. And then 0 for cations. So if I have a cation here, I'm using that plus charge, and I'm going to use that vacant p orbital on that cation to form a conjugated system. That's not going to contribute any electrons because it has no electrons in it. That's why it's a positive. And this 2 here for the number of anions, we're basically treating these 2 electrons that make that carbocation, that carbanion, we're going to use those like they are a lone pair. So for this first one, I've got 2 times the number of pi bonds, 2 times 2 plus 0. So this will give me a total of 4 electrons. For here, I've got 2 number of pi bonds, and then I've got 2 for the anion, which will give me 6. For oxygen, I've got 2 times 2 plus the 2 lone pairs in oxygen to give me 6. So these equal 4n+2 in any form or fashion. So I get 2, 6, 10, 14. This will end up being an aromatic system. Now, for simple aromatic system, which is all we really cover in organic 2, if you're really curious, go dig through the organic Reddit subthread. Somebody posted like these really cool examples of aromatics. Truth is, we measure aromaticity. That's how we know it's there. But let's say I gave you some like nightmare concoction. Something that probably doesn't exist, but hey, why not? If we did something like this, is this aromatic? Well, it meets our first condition, it's cyclic. 2, is it conjugated? Well, we got a double bond, and we can use this carbocation, and we can use one of the oxygen lone pairs to tie everything together, so it is conjugated. Now the number of electrons. We've got 2 pi bonds, we've got 2 electrons from the lone pairs, and we've got 0 from that cation, so we end up getting 6, which meets our 4n+2 rule. So this is how we do the accounting electrons. Count the number of pi bonds, multiply by 2, add any lone pairs we use to create the conjugation. If we used any carbanions, carbons with a negative charge, we're going to use that basically what looks like a lone pair on it to add 2 electrons to the count. If we use a carbocation, we're using a vacant p orbital to create this conjugation. because it's a carbocation, it doesn't have any lone pair, doesn't have any paired up electrons that are accessible for this ring, so it counts towards 0. Now the other question I got, and this is more of the Organic 2 discussion board. It was a question about how to do, because I kept seeing the same mistakes on the discussion boards, and if you look on the common response I said was that your chlorine's on the wrong molecule. So let me bring up that discussion board really quick to make sure I'm writing it out correctly. So this is the one where you end up halogenating a bunch of different compounds. So we have 2-methylheptane. 6-methyl-3-heptane. I'm sorry, 3-heptene. 6-methyl-1-heptene. And 6-methyl-1,3-heptadiene. All right, let's try these out. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Oops. So this Cl2 lambda, just a refresher, the lambda here is light. So this is UV light. And we're creating chlorine radicals, and we're going to use a restriction here that we're going to say it's a half equivalent. The reason we're putting that restriction on half equivalent is that free radical halogenation is really hard to control. So this is a hypothetical experiment. We're going to pretend that we can control the amount of chlorination. In reality, you probably get the di, tri, tetrasubstituted chlorides. On top of that, we're going to limit ourselves to the kinetic product. We're not going to worry about everything you could get by, if you do this at higher temperatures, you can definitely get some rearrangements of the double bonds. Now, think about this. Look at these prefixes, ane, ene, and ene. There is a reason why we designate an ene over an ane. So alkanes just contain saturated carbons. So why do we put the E and E at the end of alkenes? Well, that's because this is typically the thing that's going to control the chemistry the most. Not always, but generally speaking, it's going to decide what actually happens. So for an alkane, you're correct. Your first intuition should be, we're going to substitute the most substituted carbon. So we're going to get 2-chloro, 2-methyl-heptane. That's the correct first answer. So you should remember this from Organic 1. But there's also this tendency to get that knee-jerk reaction that, well, the most stable substitution point is the most substituted carbon. This is where your E and E matters. So I can put a free radical here, or I can put it here, here, here. I can put it anywhere on the molecule. The thing is that in this molecule, we only form radicals. That's it. In this case, not only do we form a radical, we have the ability to resonate in order to stabilize these resonance positions. We end up with what are called allylic carbons and allylic hydrogens. These are unique to alkenes. These are the carbons and hydrogens that are adjacent to a double bond. They are not part of the double bond, but they are adjacent to it. Because they are adjacent to it, they are more stable than their just typical radical counterparts. So even though this is a tertiary radical, it is not nearly as stable as these two secondary radicals, which can do resonance stabilization. We can kick this double bond back and forth and move the radical around. And in doing that, we displace the radical, we make it mobile, and we reduce the burden on the molecule. So this is where this E and E really begins to matter. It's going to dictate where the more stable positions are. Now, your primary, secondary, and tertiaries, that order still stands. But the caveat now is that it's primary, secondary, tertiary that are adjacent to the double bonds. So if your carbon isn't adjacent to this double bond and you're doing free radical ionization, it doesn't matter how substituted it is, it's not going to be as stable as any allylic that a carbon that's going to be closer to that double bond. So in this case, we actually have two positions that are equivalent. When we finish it, we can get let's see here, 3, 4, 5 chloro, or we can get the 2 chloro. So we get both the 2 and the 5 chloro products. Now, this radical halogenation is not going to change that it's an alkene. So it's going to be 2 chloro 6 methyl 3 heptene or 5 chloro 6 methyl 3 heptene. Same thing's true here. Even though this is a tertiary radical, this secondary radical is resonance stabilized. And anytime we can stabilize something by resonance, we're going to do it. It doesn't matter what it looks like for an alkane. The alkane is not what's carrying the parent name here. The parent name here is E, alkene. Alkenes react differently. They're going to change what your rules are. Again, secondary, tertiary, and primary are going to be more stable, so we're more likely to substitute here than if we were to resonate and put the radical here. But ultimately, we're still going to substitute near this alkene more than we're going to substitute over here. Now, same thing is going to be true here as well. We're more likely to substitute next to the diene. The complication with the diene, particularly if we go to higher temperatures, is we're going to get a lot more possibilities. But again, we're going to stop with kinetic products. So if we do the substitution here, we get 3 chloro, and here we get 5 chloro. So that's the first set of points on the discussion board. Can you name the products? 2 chloro 2 methyl heptane, 2 chloro 6 methyl 3 heptene, or 5 chloro 6 methyl 3 heptene. You get both in this case. There's no reason to favor one over the other. In this case, you get primarily 3 chloro 5 methyl 1 heptene. In this case, you get 5 chloro 6 methyl 1 3 heptadiene. Now, the second question it asks you is, how can we make, which would be the best for making 2 methyl 3 chloro heptane? Now, there was a reason for not drawing it for you. First of all, to make sure that you can still do naming. But if we draw this out, this is our product. And we're not specifying stereochemistry. We just need to make it. So if you look at this and you look at these, only one of these consistently looks like 2 methyl 3 chloro heptane. And it's this 5 chloro 6 methyl 1 3 heptadiene. Now don't let the numbering throw you off. The numbering here is just so we can draw the molecule. But if we hold these molecules side by side, this and this both produce what could be converted to this pretty easily through hydrogenation. So hydrogen nickel, hydrogen platinum, hydrogen palladium. We would prefer to go with the diene simply because we only get this 5 chloro product. The 2 product isn't very useful for this one. It's the 5 chloro we want, so we would end up getting a mixture when we finished. But the synthetic scheme here would be to say, okay, we're going to start with the 6 methyl 1 3 heptadiene. We're going to start our first reaction with chlorine light that was given to you, and then our second step is to hydrogenate. So H2 platinum, H2 PD, those types of compounds. So that's what the discussion board was going through, and it's kind of a review as well as a preface to what we're talking about with the alkadienes and the polyene material. So this is definitely organic 1. This comes up in my organic 1 courses where you do the substitutions on the allylic carbon, so it's also meant to be kind of a refresher. In fact, if you compare my organic 1 notes to the organic 2s, I literally just took the slides and copied them right in. And this is also kind of a refresher on alkene chemistry. So every single one of these you could just have hydrogenated to get the final alkane product. There's also reviews here on naming halogenated alkanes, halogenated alkenes, and making sure you understand how to name those types of compounds. Now, if you were really studious, you would have caught that these should have been the trans. I should have just called them like 6 methyl 2 3 heptene. I should have said trans. Whatever. The big thing here is making sure that you can kind of still do this type of work. So those are all the questions I've got. I'm not really seeing anything in the chat menu. I am getting some activity on Teams, so let me see if that's actually related to this course. question 30 on the homework. And again, this is for organic too. Almost there. The following set of reactions convert phenylacetylene to butylbenzene. Give the appropriate reagents for each step in the following sequences. Oh boy, a synthetic scheme. Do love me a good synthesis. So let me write out as best I can. All right, so it gives you a hint that this is being done in ammonia. So that NH3 there is the solvent, and it gives you 1, 2, oh, actually just 1. And then 1, 1. So big hint here for the first step. You've got an Na+. This hydrogen here, even though it's not drawn, is super easy to abstract. So basically, you're just going to throw sodium in the reactor to begin with. This sodium is going to deprotonate that terminal hydrogen and give you what amounts to a very good nucleophile. So this is something that is very much looking to do a substitution reaction. Bases like this, particularly because they are so big, are not so great on hydrogen extraction. So your acetylene here, this is a more acidic hydrogen than any type of alkane, so we don't have to worry about these doing elimination reactions. We don't have to worry about them doing substitution reactions. So if we take a look at this and this, the big difference here is our ethyl group. So we're going to have something containing an ethyl group and a good leaving group. My recommendation would be iodine. It will probably accept bromine as well, or chlorine. I would definitely stay away from chlorine because we're doing a hypothetical scenario. So if we got any reagent we want, let's go with 1 iodoethylene or ethane. Now from here, should be pretty straightforward. This is just a hydrogenation reaction, so H2PT, H2PD, H2N doesn't really matter. And what I'll do is I'll swap the desktop. So for step 1, definitely just Na. For step 2, something like CH3. Try again. CH2I, then H2, come on. And the comment here is just to make sure that you put in a catalyst of some sort. Platinum, palladium, nickel, they'll all work just fine. Check my work. Oh, that's really obnoxious. NaNH3, NaNH2 will also work. So yeah, for that one, it's just a matter of going through the reagents. The first one is just a deprotonating. I personally would have just done sodium, but apparently they're using the sodium to deprotonate the ammonia first. Kind of makes sense. Basically, that's going to happen anyway. So if you mix sodium with ammonia, you're going to get NaNH2 anyway. And that's going to deprotonate the terminal hydrogen. Hydrogen's going to act like a nucleophile to knock off the iodine. I guarantee you it accepts bromine as well. Maybe do chlorine, maybe it won't. And the last step is definitely hydrogenation. 35 through 37 are aromaticity problems. Could you explain this a bit? Aromaticity is still throwing me off a tad bit. It doesn't seem too consistent for me for some reason. So let me take a look at 35 through 37. So classify the following molecules aromatic or non-aromatic. Huckel's rule. If it is not aromatic, is it anti-aromatic? So when we're saying, well, let me drop the molecule first. Goodness sakes. I do apologize for this drawing, but this is not a normal shape. So when we say neither aromatic nor anti-aromatic, it means it's not meeting the one of the first two conditions. So the first condition I set for you is it cyclic? So in this case, it is cyclic. The second is it conjugated or does it stand the potential to be conjugated? So to be conjugated, we have to have either pi bonds in a circle or a combination of pi bonds, anions, lone pairs, or cations in a ring. So in this case, we've got double bond, touching a double bond, touching a double bond, touching a double bond. Now, if we add these lone pairs in from nitrogen, we create a conjugated system. So we meet the second condition here that they are conjugated. The question is whether or not adding these lone pairs creates an aromatic ring or not. So if we have the if we meet the 4n plus 2 rule, it's aromatic. If it's the 4n, it's anti-aromatic. And what ends up happening with the 4n rule here is that we end up getting electrons in non-bonding orbitals. So the system can't possibly be aromatic because we have electrons trapped in non-bonding or anti-bonding orbitals. So in this case, we have 4 double bonds, and we have the 2 lone pairs we use on nitrogen to bring it into this system. So we have 8 plus 2 is 10. And you can see this meets the 4n plus 2 rule because we have like literally 4, n in this case is 2 plus 2. So this would be an aromatic compound. And I'm just going to check my work to make sure. So this ends up being aromatic. Question 36. What is this compound? Ooh, fun. Oh man, this is a cool problem. Bit of a weird one, but it's a cool problem. I would definitely never give you anything this hard on the exam. By the way, this was also not what it showed me when I did the previews. So, I can tell you right now this is aromatic. So how does this work? Boron here is actually unsaturated. It doesn't meet the 8 electron rule. So it actually has a vacant p orbital that it can use. So our first rule is met. It is cyclic. Second, it is conjugated. This is a weird problem. I will probably get rid of it because, again, this is not the example it showed me. I would never give you a problem like this. So we are conjugated. The question is whether we meet the 4n plus 2. So the borons here don't have any electrons in their p orbitals. So for each boron, we get 0. For each nitrogen, we're going to use the lone pair. So we're getting 6, which meets our 4n plus rule. So I would say this is an aromatic compound. And that is correct. Question 37. Let's see if this is a bit more reasonable. Draw a resonance structure for the cyclopentyl dienol anion. Be sure to show all non-bonding electrons and charges explicitly. So cyclopentadiene is this compound here, and we want the anion form. And the anion, we're going to kind of cheat. I shouldn't say cheat. There's only one place we can legitimately pull a hydrogen off of, and it would be this carbon here. So is this aromatic? Well, it is cyclic. Is it conjugated? Well, we have two adjacent double bonds, and we have these lone pairs on carbon that we can use to form a ring. So it's definitely conjugated. Does it meet the 4n plus 2? Well, we have 2 pi bonds, and we have the lone pairs on that anion, so we end up getting 6 electrons, which is definitely 4n plus 2. So this is aromatic. Now, what are the different resonance forms? Well, we can kick the anion over. And just basically move it to 3 carbons away. And we can do the same thing over here. And pretty much any resonance form, because of the high symmetry of this molecule, pretty much anything that's drawn akin to that should work. Now, the big thing you have to keep in mind here is the charges. So let me draw it really quick. So I'll show you what I've got drawn on my end. And hopefully you can see this. But this, when you draw the cyclopentadiene, you can put lone pairs on carbon just fine. Yeah, that's not correct. So so if you take CH2I2, it will actually decompose into a CH2 with your lone pairs and not charged. So do make sure that you're putting the charge on there. There you go. But let me look into question 36. I'm a bit curious why it asked you that, because that's definitely not something I would have put up. Because I do recognize that identifying aromatic compounds can be very problematic. That's why your discussion board this week whoa, the next one, 38, is pretty awesome. So for 38, cyclonona tetraenol cation. So the way this molecule works is we have a cation down here and everything else. So that's where your tetraenol comes from. There are 4 double bonds. This is another good one. Is it cyclic? Yep. Is it conjugated? The answer is yes. We have a whole bunch of adjacent double bonds and we have a carbocation that we can use. So now that we've got to this point, question 3 is going to dictate, is it aromatic or is it anti-aromatic? It's aromatic if it has 4n plus 2 electrons, and it's anti-aromatic if it only has 4n electrons. So we get 2 from here, 2 from here, 2 from here, 2 from here, and 0 from here, so we end up getting 8 electrons. Well, 8 electrons does not equal 6, 2, 4, 2, 6, 10, 14, which is your 4n plus 2. So this would end up being an anti-aromatic compound. And then it asks you the same question again, this time with an anion for the next question. And with the anion, you add those 2 extra electrons in, and it ends up being aromatic. So hopefully that's kind of clarified it up for you. It doesn't become aromatic or anti-aromatic if it doesn't meet the first 2 conditions. If it's not conjugated and it's not cyclic, it's just not aromatic. If it meets the first 2 conditions and ends up with 4n plus 2, that makes it aromatic. If it ends up meeting the first 2 conditions and it has 4n electrons, then it's anti-aromatic. And again, that's why the discussion board is framed the way it is this week, is to say, do the easy parts first. If it's not cyclic and it's not conjugated, there's no point even discussing aromaticity. It's only until we get to counting those electrons, the 3rd condition, can we actually say if something is aromatic or anti-aromatic. But the first 2 conditions are the easiest ones to knock off. You're welcome. And we'll qualify all this discussion with saying we're sticking to simple aromatic compounds, aromatic rings. In practice, we measure this. So aromaticity can be seen in 2 ways. One, we'll see it in the IR, what's referred to as ring breathing modes. There are unique features of these aromatic compounds in the IR that create unique bending modes. For the NMR, we end up seeing this with basically really de-shielded protons much further down than we'd expect them to be, and carbons that are really upfield relative to them. So because these electrons are mobile, they end up generating a magnetic field. They start spinning around. If you ever like taken a bottle and spun it really fast, you can see how like the water climbs the walls. That's kind of what happens with the electron density is it starts spinning faster and faster and faster, and it actually pulls electron density away from the hydrogens as it starts to spin. It starts to like kind of stretch out away from the molecule. This becomes particularly relevant when you start dealing with like transition metals. Transition metals can be involved because they have lone pairs, they can create aromaticity. So again, it's good to be able to identify simple aromatic compounds. It makes a lot of implications about what types of reactions they can be involved in, but also realize like we're going to kind of stick to the simple stuff. We're not going to talk about super complicated, massively conjugated aromatic systems. It becomes a lot more hand wavy at that point. So graphene's an example of this. Graphene is a massively conjugated aromatic ring. That's great, but I mean, it's just kind of hard to work through how you would get to that point. So electron donating versus electron withdrawing, and how to identify which compounds will do either of those. So the easiest way to identify, big thing is to look at, so I actually had the notes, in the notes I gave you a table of the electron donating. So let me bring that up on my end to make sure what I'm telling you is correct. So electron donating withdrawing, let's say we have a benzene ring. And the three positions here, ortho, meta, and para. And if you haven't learned this acronym yet, ROMP, R-O-M-P, that helps you quickly identify where the positions are relative to that R group. So electron donating versus electron withdrawing. The critical thing here are the ortho-para positions because they are connected to the R group by resonance if it's possible. So if it is possible for R to resonate with oxygen and the ortho and the para positions, then there's going to be an effect on the reactions at those positions. Now, R does not affect the meta position. So these, R does not affect the meta position because they're not connected by resonance. So let me go down to electron donating. Aromaticity, naming benzene, connect, talk. So a common theme of your electron withdrawing groups. So your electron withdrawing groups here favor the meta position. Now, this is kind of a misleading statement. It's just how we have to describe it. What's really happening is that for any given benzene ring, all three of these positions are equal game. Now, for electron withdrawing groups, they end up making these two positions less favorable. So you can still get substitution on the ortho and para positions. This does occur. It's just that this is much more likely to occur because this R group is pulling electron densities away from oxygen, the ortho and para positions. So because benzene rings prefer to do electrophilic aromatic substitution, if you pull the electrons off of them, they don't react. So this kind of leaves the meta group as the most reactive group. So key features of your electron withdrawing groups. There's no lone pairs on the bridging atom. And what I mean by the bridging atom here is whatever is connecting this R group to the ring. So I have something like cyanide, or this nitrile group. Carbon here is the bridging group. If there's no lone pairs on it, it can't participate in resonance. And so this is going to end up having the effect that it can't participate in resonance. It can't stabilize these positions. The second is that we have large electronegative groups on R. I guess I could actually write that out, electronegative. So if carbon is connected to things, or you have like, yeah, generally speaking, if you have carbon connected to things that are super electron withdrawing, specifically oxygen, nitrogen, halogens, these become electron withdrawing groups. So basically we can't resonance stabilize, so these ortho pair positions become less stable because there's less resonance possibilities. And we have electron density being pulled off of the ring through the electronegativity of the atoms that are bound to the bridging atom. Now there are exceptions in here. There's SO3H. It still meets this condition. There's no lone pairs on the sulfur, but that's kind of like, you just kind of have to draw the Lewis structure. In terms of electron donating, come on. Your features of your electron donating. First, there's lone pairs. On the bridging atom. So what these lone pairs are going to do is they're going to create another resonance option for these orthopara positions. And the more resonance options we have, the more stable these orthopara positions get. So again, for a basic benzene molecule, ortho and metapara are all the same. What happens for electron donating groups is now we're making the orthopara positions more favorable. So meta never changes. Doesn't matter if you have electron withdrawing or electron donating. The question is what happens to the orthopara positions. For electron donating, these become more and more favorable. So we do get some meta substitutions, but mostly it's orthopara. And if we're being honest with ourselves, it's mostly para because of steric effects. Now, the other thing is that we don't have no strongly electronegative atoms. And we're not talking about the bridging atom. What we're talking about are things bound to the bridging atom. So if the bridging atom is more electronegative than what it's bound to, this ends up becoming an electron donating group, and we start favoring the orthopara positions. So one of the first examples in the notes is NH2. Nitrogen's more electronegative than hydrogen, so it's got plenty of electron density. And this nitrogen has lone pairs which can participate. Now, there are kind of weird exceptions to this. So if you look at the table on page 98 of the slides, an aryl group, so another benzene ring is going to become electron donating, but there's no lone pairs on a benzene ring. The other is the alkenyl, the vital groups. The reason why these become more electron donating is conjugation. So if we have a whole bunch of conjugated double bonds, even with something like an ester, actually an ester would be a bad example. Ceralkoxy groups. Oh no, okay. I'm confusing myself. So keep it simple. If we have any type of conjugated carbons beyond this, these are going to be electron donating. It's not, again, I'm kind of breaking this. There's no lone pairs on the bridging atom. What's more important here is that we kind of have some type of pi system available. That's the big kind of picture about electron donating versus electron withdrawing them. If it's lacking a lone pair on the bridging atom, it's probably electron withdrawing, especially if the things bound to that bridging atom are super electronegative. They're just going to pull electron density off. There are exceptions. That's why we have the tables. Some of them are actually debated. Even within Francis Carey, halogens are debated. So something like a halogen, it has lone pairs which can participate in the ring and stabilize the orthopara positions, but it is an electronegative element. It's likely to pull electron density towards itself, so that would make it weakly deactivating. They get kind of debated. But yeah, hopefully that kind of explains it. You're welcome. Other questions? Yes, so labs for, as far as we can tell, are going to be on campus for the rest of the semester. For Orgo 2, first thing we're going to talk about is we're going to go through how to assemble lab glassware. I've got the test one study guides from Organic 1. We're going to go through some examples on how to do 1H NMR, IR, and mass spec. And then it's kind of an open discussion from there about what other questions you have. So I just got a question. Can you explain the optical activity example on slide 10 of the analytical techniques for Orgo 1? So optical activity is a weird beast. And I say it's a weird beast because the theory itself is quite simple. The formulas get weird and you have to be very careful about units. So the formula that's given on part 10 of the optical activity, and this is really the more relevant formula here. Alpha equals alpha D times L times C times EE over 100. Now, D here is going to refer to the dextrolevatory. Dextrorotatory. So for the D rotation, this is going to be clockwise rotation. L here is the path length. For this formula, this is in centimeters. So basically when you do the optical activity measurement, you've got a tube that contains your sample. It has some given length L. You've got your polarimeter that the light passes through. You've got a detector on the other side. This measures the angle alpha of the deflection. C is the concentration given in grams per milliliter of whatever solution you're working with. E is the percent enantiomic area activity. So it's the difference between the percentage of the D form minus the percentage of the L form. Now, the 100 is in there so that you can put the actual percentages in there. So you wouldn't do like, if it was, the EE was 30%, you wouldn't do 0.3, you would do 30 and divide by 100. So that 100 is, because we report EE in percent, this just kind of makes it a little bit easier in terms of that formula. Alpha D here is a physical constant. And so this would be the rotation if you had a 1 centimeter tube with 1 gram per milliliter and you had 100% optical activity. this would be how much it deflected. So that's where this formula comes from. Now I show you a derivation. The derivation is not necessarily important. For me, it helps it when I see things, but if you don't really need to see the derivation, that last formula on part 10 where it says alpha D times L times C times EE over 100, that's the more relevant formula. Now, there is a complication with this formula, and this complication comes from the fact that old, I need to update the slides. Let me check. I think that was a correction that didn't make its way through. So I was about to bring that up. Some textbooks do L in decimeters. And there is a corrected formula that I give you that does not use decimeters, and it's the one I recommend you use. So let me check the notes, and I'll send an email out just to verify. I may just, but I didn't update the notes in the development shell, but I updated them last semester. Old optical activity devices, and I'm not joking old here, like made in West Germany, I've seen them. They use 10 centimeter or 1 decimeter glass tubes. The thing is that we don't use those anymore. We use variable length optical analyzers. So it's actually a lot more convenient now to work in centimeters. The other thing is that a milliliter is a cubic centimeter. So the decimeter units here don't quite cancel out, and you end up with weird conversion factors, factors of 100 that pop up in the, make sure I make this up. You end up with weird, like multiplying or dividing by 100 to make the units work out. So let me go through, and I'll send out, I'll either make an announcement tomorrow during the live stream, or I will send out an email to you to let you know. But yeah, definitely that L, we don't need to be working in decimeters anymore. We really need to get away from working in decimeters. The formula actually gets a lot simpler if you're not working in decimeters. But yeah, it's weird because your book does talk about using decimeters a lot, and then it gives a 1 paragraph explanation saying, well, actually it's a lot easier to work in centimeters, and then never brings it up again. Centimeters is the more relevant unit. I'm guessing most of you don't even know what decimeters are off the top of your head. And really the only reason I know it is from decibels. All right, other questions in the remaining 3 minutes? So for the CIP rules, if you have a double bond, so we have something like this versus COH2, we consider not the atoms that are bound, but the bonds to those atoms. So for something like an aldehyde, it would actually be COOH versus this one, which would be COHH. So each bond here corresponds to the oxygen. So a double bond just counts as that atom twice. And if you have a triple bond, that triple bond would count as that atom twice, or that atom 3 times. All right, so that's the end of the live stream. Again, if you have questions, I have one tomorrow, I have one Friday. Just send me an email in advance. Otherwise, I will see several of you in lab tomorrow.